Hey guys, today we're taking a look at power functions. Now, power, first of all, is an expression of x to the n, where x is considered the base and n is the exponent. So here's a few examples. 8 to the third power is 8 times 8 times 8. This is known as the expanded multiplication form. Now, remember, 8, the base, and 3, the exponent, just tells you how many times you multiply the base by itself, and that results in 512. 2 to the fifth is 2 times itself 5 times, and the result is 32. Now, this is read as 2 to the fifth power. Now, there are some important power functions that we're going to want to commit to memory. The first power function you've known for a long time, and this is known as the identity function, and it's simply y equals x, or in other words, f of x equals x to the first power. So this is that 45-degree line in which all the points 0, 0, 1, 1, 2, 2, negative 2, negative 2 lie on that graph. The next important power function is the square function. So this is f of x equals x squared. Again, you can see that it passes through the origin. The points negative 1, 1, and 1, 1 also lie on this graph. The next important one is the cubing function. This is y equals x to the third power, or y equals x cubed. Again, you can see that it passes through the origin. Negative 1 is on the graph, and 1, 1 is on the graph. So let's pause here and take a little look at some other power functions on Desmos. And there's a few things that we want you to look for, namely some patterns in those power functions. So here's our function f of x equals x to the n, where x is our base and n is our exponent. Right now our exponent is set to 0, and you can see that we have a horizontal line that goes through the point y equals 1. So let's go to make our exponent 1, and here's our identity function. Again, you can see that it passes through the origin. Negative 1 is on the graph, and 1, 1 is on the graph. Right now, what we're going to say is that the power of this function is odd. Let's increase our power, our exponent, to 2. Now we have an even power function, and you can see that we have a parabola that opens up. Again, it goes through the origin. Negative 1, 1, and 1, 1 is on the graph. Negative 2, 4, and positive 2, 4 is on the graph. Let's change it to 3 now, and again we have an odd power function. If we zoom out a little bit, we see that we go through the origin. We have negative 1, and 1, 1 is on the graph, but we also have 2, 8, and negative 2, 8. Well, what happens when we make this an even number again, or an even power? We see that we now have x to the fourth. We still have negative 1, 1 and 1, 1 on the graph, and it passes through the origin. If we zoom out just a little bit further, we see that we have negative 2, 16 and positive 2, 16. Well, there's some definite patterns that we see emerging here as we change between odd powers and even powers. So as I drag this out towards 7, 8, 9, and 10, you can see those patterns emerging. All right, so back to our notes a little bit now. As we increase the power of those power functions between odd and even powers, we definitely notice some patterns there. Some of those ordered pairs that were on the graph when n was even, well, it always passed through the origin, and it always passed through negative 1, 1 and positive 1, 1. Now, another way to say that is represented in just general terms, and general terms here are when it passed through x, it also passed through the opposite y. Let me just check my notes on that. Let's back up on that. Here we go. When it passes through the xy, it also passed through negative x, positive y. Okay, so that's for an even function. Now for an odd function, it also passed through our origin. It passed through negative 1, and it passed through positive 1, positive 1. Now, in general, it passes through all x, y coordinates, and it passes through negative x, negative y coordinates. So in other words, if the point 2, 4 is on the graph, then the point negative 2, negative 4 is also on the graph. All right, now our domains. Remember, our domains are our x values, and now for an even function, our domain was all reals, and likewise for an odd function, our domain is going to be all reals. However, for range, for an even function like the parabola, our range was all reals greater than or equal to 0. But our range for an odd function is still going to be all reals. The quadrants of our graph, for odd, our quadrants were always quadrants 1 and 3, and you can see that here in our examples up at the top. And therefore, for an even function, we should do our even function first. We have quadrants 1 and 2. So quadrants 1 and 2 for an even function. And then for odds, we're quadrants 1 and 3, which are the two odd numbers out of 1, 2, 3, and 4. All right, now let's talk about symmetry. Symmetry just means how you can map the graph back on itself. So for an even function, our symmetry is going to be a reflection symmetric line over the y-axis. So we'll say reflection symmetry over the y-axis. And then for an odd function, you'll notice that we can rotate 180 degrees around the origin and have that graph map itself back on top. All right, so we're going to say rotation 180 degrees around the origin 0, 0. All right, let's take a look at a few applications of power functions. Applications often arise out of probability problems. So suppose a probability of an event will occur is P. Let A be the probability that the event will occur 5 times in a row. So in order to write this formula for A, we say that the probability that an event will happen 5 times in a row is the probability of it times itself 5 times. So in other words, that's probability of P to the 5th power. So here's a little bit more of a concrete example. Let's say, what is the probability of rolling a die, a 6-sided die, and getting a 6? Well, that probability is 1/6. So what's the probability of rolling that die 3 times and getting 3 6s in a row? Well, that's 1/6 to the 3rd power, or in other words, 1/6 times 1/6 times 1/6, which represents 1 out of 216. Now as a decimal, that is 0.00463. So it's a very, very small percentage that you'll actually get 3 6s in a row. All right, one more example here on probability. Suppose a certain bowler can roll a strike about 20% of the time. What is this bowler's probability of beginning a game with 6 strikes in a row? So again, our probability here now is given in terms of percentage. As a decimal, 20% is 1/5. And if we want the probability that he can get that 6 times in a row, that's 1/5 to the 6th power. So that's 1/5 times 1/5 times, well, you get the idea, right? 6 times. So there's 4, 5, and 6. And in terms of a decimal, that's going to come out to be 0.000064. So a really slim chance that you're going to roll 6 strikes in a row. All right, in example 3, it says to refer to this graph here. It looks like we have a power function. You can see that it passes through the origin. It passes through 1 over and 1 up, and it also passes through -1, -1. It appears in quadrants 1 and 3. So it looks like the shape of this graph is going to suggest that this is an odd power function. We want to give the domain and the range. Well, the domain here is going to be all real numbers, and same thing for our range is going to be, again, be all real numbers. All right, now it says if the point 3, 2187 is on the graph, what other point must be on the graph? Well, that point is going to appear over here in the first quadrant if I go over 3 and up 2187. And if it's odd, then I know the point -3, -2187 must also be on that graph. Finally, it says, what is the equation of this power function? Well, remember, x is our input, y is our output, so x to some power must equal 2187. Or you could say negative x to some power must equal 2187. Next, you're just going to try guessing. So maybe you want to try a 3. 3 cubed actually is 27, so we're quite a ways away. Maybe next you want to try 5. 3 to the 5th is not quite there, but the next time you try an odd power, 3 to the 7th, you'll see that it's 2,187. So we're going to say that this power function is y equals x to the 7th power. Alright, our last example for today says to find the power function such that negative 381 and 381 are both on the graph. So if you go back to our notes, you'll see that it's an even power function that has the coordinates x, y, and negative xy. And this means that they're a reflection over the y-axis. So I'm looking for some power function where n is an even number. So again, you can plug in our numbers here. 3 to the n must equal 81. So what power would I raise 3 to in order to get 81? I can start off with the first even number, 3 squared. Well, I know that that's 9. And let's try the next even number. Well, that's where I get 3 to the 4th is equal to 81. So I say that my power function here, that would give me these two coordinates, would be y equals x to the 4th power.